Hello. Um, I'm at home, so I wouldn't normally be wearing the mask, but I just want to encourage everyone to do that for as long as we need to. I'll go ahead and take it off. Be right back. I'd like to thank everyone uh, for joining the webinar and for your interest in engineering at Virginia Tech. My name is Carl Dietrich. I work in the Electrical and Computer Engineering Department, the Bradley Department of Electrical and Computer Engineering. Um, and specifically, I'm a research faculty member in the Wireless at Virginia Tech group. So we do research that relates to uh, wireless communications and other applications of radio technology. And today, today we'll be talking about some topics that are seemingly unrelated, but in fact, there are some connections between them. So, and some that I've found over the years that I wasn't expecting myself. But I'll go ahead and start the slide presentation. And just in case it gets loud where I am, I'll be putting on headphones. But I'll also keep an eye on the chat to the extent that I'm able to see it, just in case there are any questions, and we'll have some time at the end for questions. Thanks again for joining, and I'll go ahead and start the slides. Okay, so this talk relates to spectrum sharing and cognitive radio, and specifically aspects of that related to research, infrastructure, and education. And as you can see from the graphic there, perhaps the emphasis here is going to be on experimentation, so experimental research. But while the title, I hope it's informative or will become more informative if it isn't already. That's maybe kind of a boring start to the talk. So we're going to talk about it a little different way, where we'll look at radios, robots, video games, and antennas. And question is, what is the connection between these things? So, and you may see a few of these graphics later in the presentation, and maybe that'll help all of this to make more sense. So we have some things on the left that go way back, some further back than I go, but we have an old school science fiction robot here, and also an early video game called Pong, which is sort of like a table tennis game that involved moving these paddles up and down to a ball, which is just a few pixels that would travel back and forth. So these on the right are some more recent graphics related to projects at Virginia Tech. This slide's a little bit autobiographical, but I was in a position similar to the one you are, starting engineering school. I was interested in finding a major. Video games were pretty new at the time and interesting, I thought. So my initial thought was that I'd like to learn to develop video games. But that's not something we did in the first few years of engineering school. And I was pretty busy with classes that I had. Then I went to work for a few years and went back to graduate school after that. In graduate school, I did some work with what were called smart antennas, and this is a combination of using multiple antennas and using some signal processing, doing some math to process the received signals. It's the general technique goes back to the 1960s or 70s when it was done with analog circuits. More recently, it's much easier to implement these kind of systems using digital techniques in many cases. And at the time I was doing the research in graduate school, we used an approach that's come to be called software-defined radio. And the term was already around at the time. I didn't realize that's what I was doing, but I just wanted to be able to process the data that I recorded using actual antennas. And at the time, the most practical way to do that was to use a digital audio tape recorder and convert the signals from radio frequencies at about 2 gigahertz down to audio frequencies that could be recorded on 1 or 2 digital audio tape recorders, and then process the data offline afterwards using MATLAB and tried out those various signal processing techniques. More recently, I've done some other research related to radio wave propagation, which is just the way that radio signals are affected by their environment, and that can be characterized by the relative strength of the signal that's transmitted and then the signal that's received at some other location. And there's various other statistics that characterize radio environment and different kinds of models that have been developed, which are either equations or probabilistic expressions that predict or approximate the effect of an environment on radio signals. I also became involved in research related to software-defined radio, which can now be done in real time. It's come a long way since the time that I started. Also, I had the opportunity to participate in a summer research experiences for undergraduates program, or REU, that was sponsored by the National Science Foundation. And I participated as a mentor for a couple of years, working with groups of students on research projects over the summer or during the summer. And after a couple of years of that, the person who was leading the site left for another job, and so I became more involved. And then the next year, the person who had taken over running the program left, and I actually ran that for about 3 years, including 2 summers in which there were students. This diagram on the right is showing just some of the research that I did in graduate school. But more recently, these kinds of techniques are being included in 5G communications. The 5G radio frequency bands include some that are at high enough frequencies that it's practical to use multiple antennas and fit those in a handset or a smartphone. So those techniques will become increasingly practical and useful. Related to 5G and to wireless communications in general, there's another trend which is radio frequency or RF spectrum sharing. The idea here is that we are constantly inventing new applications for wireless communication that require higher rates of data transfer for more users and more devices. Some applications like text messaging don't require very much bandwidth or very wide range of frequencies. Others, such as video and high-speed file transfers, require much more bandwidth. And with the increasing definition of videos and increasing number of devices and users, there was a prediction of a spectrum deficit. Now, by now, we should be in this red area. And although wireless communication hasn't ground to a halt because there's not enough spectrum, there's still an advantage to having more spectrum or a wider range of frequencies, a different and greater selection of frequencies that we can use to enable all the kinds of applications that we'd like to have. And those include things like video, but also Internet of Things. Although that may be a relatively low data rate per device, there's a prediction that there could be 1 million Internet of Things devices per square kilometer. And in fact, 5G or fifth generation cellular is intended to meet that demand. So the cumulative use of the spectrum by all of those devices will be significant. There are also other kinds of machine-to-machine communications and intelligent transportation systems, self-driving vehicles, unmanned aerial systems, drones, and so forth. All of these applications will require increased capacity. And informally, we often refer to capacity as bandwidth. So capacity is the maximum theoretical data rate, and then the practical data rate that we can achieve. It's closely related to something called bandwidth, which is the range of frequencies that are used for communication. And we'll get into that a little bit later in the talk. So we want to use the radio frequency spectrum efficiently. The radio frequency spectrum is a range of frequencies that are practical to use for communication. And it's a limited range, and partly due to physics, because some frequencies just work better. The propagation or the ability of radio signals to travel over distances is better at some frequencies. In some cases, having the signals not transmit over too great a distance can actually be an advantage because that avoids interference to neighboring users. On the other hand, in addition to these physical limitations, there are limitations of our technology that make us better able to use some of these frequencies than others, resulting in a limited range of frequencies that are really practical to use. And they have to be shared among all of the different applications, from broadcast radio and TV stations, radars, cellular communications, and others. So the traditional approach to doing this is to allocate specific frequencies for specific services, and then to assign frequencies to specific users, such as a TV station in a particular region. They would, one TV station will get one frequency, or perhaps a few frequencies to use. Their competitors in the same market or in the same area would be assigned other frequencies so that they don't interfere with, so that the stations don't interfere with one another. And at some distance away, far enough that that interference won't occur, the frequencies can be reused in another city or another location. And the same kind of approach is used on a smaller scale in cellular systems, where the different cells don't interfere with one another, and different providers typically would use different frequencies in a given region. However, the graph on the lower right here shows that in many locations, not all of these frequency bands are heavily occupied over time. And in fact, over this average of locations, and some of them were rural or parkland, some were, there was actually a radio quiet zone also, but there are also places that some of you might be familiar with, certainly have heard of, such as New York City, such as Tyson's Corner in Virginia, Arlington, Virginia, some fairly built-up areas that you would expect to have high spectrum usage, and those were about half of the locations. Also, Vienna, Virginia, kind of a suburban location, but pretty busy. Averaging all of those, the usage was still well below half, around 25% at most, and in some bands it was much lower. So while we have this idea of a spectrum deficit, we also have all this unused spectrum, all these unused frequencies that could be used for wireless communication and whatever type of application we might have in mind, if we had a more flexible way of using the spectrum. That's what this dynamic spectrum sharing is. The federal government has identified an opportunity to enhance the economy by sharing some of the spectrum, some of the frequencies that are dedicated to use only by federal systems, and making that available for commercial use as well. And with dynamic spectrum sharing, it's actually possible to do that at the same time, not at the same instant in the same location, but it's possible for those different systems to coexist within a band of frequencies, and this will enable much more efficient spectrum use. And one reason we care about this is because the radio frequency spectrum is a limited resource. It provides can be used to provide valuable services. So its value is reflected in the amount that service providers have to pay for use of the radio spectrum. The Federal Communications Commission auctions blocks of the radio spectrum to companies who would do things like provide cellular service. And an auction about 6 years ago now raised over $42 billion. And another thing to keep in mind is that the companies who paid this money expect to make a profit from their investment. So the actual value to those companies had to be more than this, or they had to believe that they would make back this money and then more. So that spectrum is very valuable. So if we can do something like this, the ability for a signal to hop to unused band of frequencies and perhaps transmit more data, that's really a valuable capability. And there are different ways to do this. One would be for the radio that's transmitting the signal to also listen with its receiver and find unoccupied ranges of frequencies that it can use. And another approach is to have some kind of central coordination. So either of those approaches or some combination have been tried and are being used in various frequency bands now. There's something related to this called cognitive radio, and it's the idea of having a radio that has some kind of intelligent controller. And we're not talking about human-like intelligence, but its capabilities are modeled on human cognitive capabilities. So it would involve things like memory and so forth, as we'll see. But a radio, one thing that okay, so as engineering students selecting a major and selecting a specialty, at least when I was in that position, I liked being able to see the results of my work, see what was going on, and frankly, a radio doesn't have any obvious moving parts. Sure, there are electrons and things, but it's not that easy to see what it's doing. On the other hand, you think of a robot, well, that'll move around and you can see what it's doing. That's a lot more engaging, perhaps. At least it's got more visual interest. But it turns out that a cognitive radio is a lot like a robot. It meets this definition of a robot that you see at the bottom of the slide. It's just that the physical environment in which the radio exists and operates, although it exists in three-dimensional space, but it's also operating in this radio frequency environment that you can't see with just your eyes. And like a robot, though, it has a type of controller, which we call a cognitive engine. That's just the terminology that's used. And some of this already exists. So this is an idea that was proposed around 1999 by Joseph Mottola, who later became a faculty member at Virginia Tech. And that was about 20 years ago, a little more than 20 years ago. And in some ways, it may seem that cognitive radio has taken a while to become prevalent. If you look on the internet and you want to buy a cognitive radio, there may not be very many products out there that are advertised that way. On the other hand, many of the capabilities in cognitive radio actually are incorporated into things like Wi-Fi and cellular standards. There are many definitions for cognitive radio, and they have various capabilities in common. There are several that are unique to the different definitions. They're not all identical, but one of my colleagues identified these common features that all the definitions have. And one is the ability to adapt to the environment and to make autonomous decisions, and some ability to sense the environment. And then based on all of that, to make adjustments to the way the radio transmitter works. So we've seen this idea of a cognitive radio, and we have a little bit more to see about that. It's not really easy to visualize what it's doing or just to imagine it necessarily. So part of what I'm doing is with some colleagues, some other faculty, and some students, and some other people who work at the university, we're working to make it easier to see all of these capabilities in action. And that's good for education. It's also good for research. So the cognitive radio has this ability to observe its environment, the outside world, and then analyze what's going on. Based on that, make some kind of decision, possibly do some learning and planning, and then act by changing its transmission parameters if needed. The transmission parameters would be things like the frequency on which it's operating, the bandwidth or the range of frequencies that the radio is using, the transmitted power, and some other things related to how fast it tries to send the data. And its ability to do that successfully just depends on the quality of the channel, things that are measured by the relative strength of the radio signal at the receiver to noise or random signals or interfering signals from other transmitters, and also some other channel effects can determine the maximum data rate that can be achieved. There's also something called software-defined radio. I mentioned it earlier. Here's a little more thorough description where we have an antenna. We're looking at a receiver primarily, but in this case, actually also a transmitter. We have flexible radio frequency hardware, things like amplifiers that increase the strength of a signal, things like filters that selectively pass some frequencies but not others, and can be used to reject interfering signals on nearby frequencies, and some other hardware that allows for things like changing the frequency of a signal or sharing an antenna between a transmitter and a receiver. The arrows coming out of this flexible RF hardware, that's the receiver. The arrows going from left to right, the arrows going from the right to left are the transmitter. So the next step is analog to digital conversion, changing the signal to numbers that can be processed mathematically by a computer to do signal processing. Then we can do things in software like channelization, that is dividing the signal into frequency channels, just narrower ranges of frequency. So perhaps the signal we're receiving isn't from a single transmitter. It may be that this software-defined radio is at the cell tower and it's receiving signals from multiple phones, and maybe they're using different frequencies. So we do that kind of channelization. We do more signal processing at baseband, which would be after these signals are converted to a low frequency, we can process them. There's hardware that does that, things like field programmable gate arrays or FPGAs, DSPs, kind of special purpose microprocessors that are good at digital signal processing, application specific integrated circuits, GPPs, general purpose microprocessors like you might have in your laptop or desktop computer. And then on that hardware, we have software that runs, and that really goes. That actually is the motivation for using software-defined radio in the first place. It's kind of a hassle to move to this new way of designing radios, but the advantage that you get is flexibility. So you can use the same radio to implement different communication standards just by changing software the same way on your computer you could run a word processor or a spreadsheet or a web browser. Okay, so dynamic spectrum sharing. The reason we were talking about cognitive radio and then SDR, which makes it easier to implement or build a cognitive radio, is that can help enable spectrum sharing. And there's some trade-offs to be considered, kind of some research issues. I'll kind of speed through the next few slides on research, but one thing is, if we're going to build a cognitive radio or a dynamic spectrum sharing system, we want to know how well it works, right? That's important for researchers. We want to know because we want to make it better. We want to improve our approaches. Other people like regulators want to know because they want to know that the radio will act in a predictable way so that it won't interfere with other radios. For acquisition, that's just purchasing. You can imagine a government agency or a big company like UPS or something. They might need radios and they would buy a lot of them, but they want to make sure that they're spending their money on a good product. So this is where kind of a consumer reports kind of product comparison testing would be useful. And then after deployment, we want to make sure those radios are still working as they're intended while they're in the field. So there's some research to be done in this area too. And one way to do that is to apply some of the same methods that are used for basically that people use to test us when we take a multiple choice test. Those questions have been calibrated for difficulty with other people who've taken the previous test. Like when you take a test, you would typically get some questions that are used to measure your own performance, and then some that aren't being used for that at the time. They're kind of experimental questions that the test developers put in there just to get a lot of people to try the questions and see how well they predict performance on the test. So if your performance on that day is good generally, and you also perform well on the experimental questions, then and enough people do that there's a good correlation, then they would become part of the next test that somebody else might take at a future testing session, maybe another year or something. And so we want to do something like that. A lot of research has gone into developing those kinds of approaches, and we'd like to do something similar to that with the radios. And we need to look at how do we measure the performance? What do we care about? Like how fast the radios adapt, or how accurately, and so forth. And so the idea is that we would develop test scenarios, calibrate them with a group of radios that we'd actually designed to have particular characteristics, and then they should work. Ideally, they'll work on new radios that we're not familiar with, that weren't used to design test. And just what does a test look like for a radio, right? It's not going to have to solve a math problem or remember vocabulary, but what we want the radio to be able to do is to adapt to a different signal environment, just meaning there's some number of other transmitters in the same environment, and each of those is sending the signal over a channel that's just sending it through space, and there might be obstacles there that are, like buildings or terrain, and so forth. The radios might be moving, in which case that's part of the channel. And then we add all of these signals together at the and just as they're added together at the antenna of the receiver, and we have what we call a data source and a data sink. That's just data is provided by the source. The transmitter transmits it over a channel. There's some other radios that are interfering with it from the perspective of that radio. And then at the receiver has to try to sort all this out, convert the signal back into bits, and then that data can be compared with the original transmitter data to assess performance. To help do this kind of research, we've developed what we call the CORNET Testbed, and the testbed's just, in this case, a collection of software-defined radios and servers that were originally distributed throughout one of the buildings on the Virginia Tech campus in this way. And again, we were talking about cognitive radio, and then ideally we'd have networks of these radios, and the testbed was built to provide that capability. Just so we could see what the radios are doing, we need to be able to display in real time their activity. And one way we did this was using a three-dimensional way of visualizing these in a web browser, where we have on the horizontal axis, this is frequency. So you can see lower frequencies are on the left, higher frequencies are on the right. And going from front to back is time, and so the current signal would be displayed in the front, and then you'd see it move towards the back, and the height is proportional to the signal strength. We still have the code for that, but more recently we've been using a two-dimensional plot. It doesn't look quite, perhaps doesn't look quite as interesting, but it's actually easier to read. But we can try, and we can use multiple ways of displaying the spectrum. We also developed something called the Cognitive Radio Test System to enable these kinds of experiments. And I'll show you that actually in a few minutes, or I'll show it to you in action. I won't show you all the code, but we'll see. So the idea is that is an experiment management framework that we use with our testbed, that collection of radios and computers. And we give each of those radios that are sitting above the ceiling, we give it kind of a personality by using particular software-defined radio signal processing code or programs that make that radio act as a transceiver. Perhaps it looks like a wireless communications transceiver, maybe something kind of like a smartphone or a Wi-Fi access point or the Wi-Fi card in a computer, or maybe it looks more like a radar and it acts in the role of a radar. So we can, just by giving those different radios these different roles, we can run a variety of experiments. And for spectrum sharing experiments, we can also use a spectrum access system, and we're building an open source spectrum access system that will do the scheduling. So the radios might sense the signals around them and decide what frequencies to use, or depending on the experiment, they might also, or instead, communicate with a central database that makes those frequency assignments for them. We did some tests with CRTS where we were able to measure things like the ability of a lower priority user to basically vacate a channel quickly when a high priority user starts transmitting. That's a requirement for sharing the spectrum. We could also look at the primary user, that high priority user, and see how well their data rate stayed consistent depending on the presence of these lower priority or secondary users. And even when they were sharing the spectrum with the other users, they were still able to achieve nearly the same data rate, but with more variation. So we were able to do that kind of experiment. We also had a test with periodic interference, where we had another radio signal that would turn on and off, and it would be on the same frequency as the signal of the transmitter that we're trying to receive, and predictably the more packets of data were received correctly when the interferer was off. So these are just some experiments that we did to validate the CRTS. Now, this is the spectrum access system that I mentioned. This is more people involved in that project have mainly a computer engineering background. It's a software intensive project, but it's also important to understand the application. These are just some other things that we can do with CRTS and humans. We'll actually do this in a few minutes. 2D and 3D spectrum plots. Again, we're going to use these 2D plots and see those robotic radios in action. So if you look at the radio itself, it's just sitting there, but you can see what it's doing in a web browser with the right visualization. And we had a couple of projects, one from the National Science Foundation, and the idea there was to have interactive experiments that use the testbed and let the students control radios manually in a web browser and see how well they operate. We had a related project sponsored by the Office of Naval Research, and the idea there was similar, except that instead of operating the radios manually, we would let the students edit, or the students or professionals edit code that would be the controller of that cognitive radio, and then run some experiments and see how well that performed. And we have a few other educational projects, including a new project from ONR that kind of pulls all of that work together. So we did make progress on those, but we're really getting it all together in this current project. We've also, along the way, we've also run a spectrum sharing radio challenge, an international and high school level one. And so that acronym spells out SHARK. So we had one of the people working on the project made a radio signal that looked like a shark fin in the frequency domain, the spectrum plot there, and it actually had that sweeping in frequency, so it looked like a shark swimming through this random noise part of the radio environment. This other, at the bottom center, this is a simulation in which a student or user would play the role of the spectrum access system and respond to requests to use various parts of the radio frequency spectrum and assign those frequencies in a way that doesn't overlap with known use by the primary users or the high priority users. We also have something kind of related to this. It does also involve software-defined radio and wireless communications. It's a multi-year undergraduate project that's supported by the Virginia Space Grant Consortium. And that involves an antenna range, which lets you measure the directional characteristics of an antenna by rotating the antenna while it's receiving a signal transmitted by another antenna, and you'll see how the antenna responds at different angles. You end up with a polar plot, in polar coordinates, which you've probably seen in a math class, and we actually use those pretty extensively in antenna engineering. We even use spherical coordinates and some of the other things that may not have as many obvious applications when we first study them. So this is an undergraduate project. There is one graduate student who's been helping, but the goal of the project is to besides achieving its technical goals, the idea is to have a multi-year undergraduate project where mainly sophomores through seniors would be working on the project, and as new students come in, they learn from the students who are experienced in the project. And then the specific goals of the project will actually change over time as previous goals are achieved. One of our alumni got his PhD at Virginia Tech, is now faculty member at another university in Utah. And he developed this with some colleagues there and made a prototype available to us. We're doing some additional work to make it available online so that the range can be operated online. We've got that working now in a remote desktop environment, but we're going to have a web page so that no special software is needed to connect to it. And we have big plans for expanding this nationwide. You could imagine a pool of these antenna measurement systems, maybe each set up with a different kind of antenna. And as part of the lab, a student could go to the web page. It's kind of a gateway to all of these, find out which ones have the kind of antenna the student wants to measure, click on the picture and make a measurement, download it, and provide that as part of their report with some description of why they think the antenna is working as it is measured. Other things we could do is use this as combined with 3D printing. So some of the parts of this antenna range are 3D printed. We can also 3D print the antenna patterns themselves and use that as an educational tool too, so that you can actually pick up the antenna pattern. And for people who perhaps learn best or would be helped by holding up the antenna and being able the pattern and being able to rotate that and see how it relates to the antenna itself, that would be really convenient. And I think that would be, it might be especially true for people who have visual impairments, but I think it may be true for many, if not all of us, that if we have one more way to look at a problem or a phenomenon, that's another way to learn that can help. So we want to just keep improving the range over time, and also do some antenna pattern measurements using UAVs or drones. So I would like to have some time for questions, and we will. I'll be able to stay on. I wanted to show you a few of the things that we've done. So we were talking about that CRTS, cognitive radio test system. We talked about the Testbed and those various educational projects. And so we have some exercises that we're integrating within online modules, online educational modules or learning modules. And those give some kind of hands-on experience during online education. And I know we've been forced into more of that over the last year. But it's not an entirely new thing, and it's not going to go away, even when we're in a better situation than we are right now. Now, here's I talked about that capacity or maximum. This is the theoretical maximum data rate, and you can see if perhaps I can expand this a little bit. You can see here it's 191 megabits per second. Here we have the signal in that frequency domain plot where we see the signal's frequency use, and we see how strong the signal is on the vertical axis. On the right, we have some the dashed line is the highest rate we can actually achieve, but to do that, we have to select the right kind of modulation and coding combination. Modulation is just the way the radio turns bits into a radio signal, and coding is that some bits are added in a strategic way to provide some redundancy, meaning that even if not all the bits are received correctly, as long as most of them are, the signal, the errors can be corrected and the original bits can be recovered. And some of these are kind of slow, but they work really well. They're robust. They work even when the signal isn't very strong. Some of them need a very good signal, but are very fast. So strangely, after going back to the beginning of the presentation, after all this time, when I had completely really forgotten about this idea of developing video games. Well, I'm not doing it myself. I'm managing the project, but this project is now actually developed something that looks a lot like a video game. And here, the signal would normally increase in strength or decrease in strength depending on the channel and things like that. We added some complexity here by changing the bandwidth to just the width of the signal. You can see here I'm using the very robust, conservative, but slow way to send data, and it's achieving a data rate or spectral efficiency. The number of bits per second per hertz of bandwidth is kind of at the low end right now, right, on that plot. We can try the higher rate, kind of a more aggressive combination of modulation and coding. And that's good, except that when we get past that dashed line, that means we don't really have good enough signal quality for that to work, so that the receiver won't be able to recover all the correct bits. So that's pretty useless. So to make this really work, we have to adapt and try to stay under that that dashed line. And okay, and so this I'll go ahead and share with you. This is very scalable, so everyone can, many people might be able to use this at once. So I'll go ahead and share a URL with you in case anybody would like to use it. Now, somebody had a question. Doesn't the typical device that is part of the Internet of Things usually have a very short range connectivity, limited to the household, allowing multiple devices to share the same frequency in an area? And it would have relatively short range and use relatively low data rate. But at least some of those IoT or Internet of Things devices would be communicating with a cell site. But again, they wouldn't. No one of those devices would use as much of the capacity or the data rate as a typical video or perhaps a voice conversation. Okay, so I'll go ahead. If we have the chat here, it looks like we do, because I'm receiving chats or chat messages. I'll just go ahead and send this URL. Actually, I'll do that at the end of the talk, just so we're not all on here at once. But I'll do that at the end of the talk, just in case anybody would like to use these exercises. And let's see, we've got another one, basically the same thing, the same problem, but now you can write code to control the radio. And in fact, that code is already written. So you could try something like just randomly selecting the, and we've got an extra plot in here too. Now we've got something that'll be the data rate history over time in that center plot. So we could try just randomly selecting, just kind of guessing what data rate or what combination of modulation and error correction coding we should use. And sometimes it works and sometimes it doesn't. So we see this history of, sometimes we're doing pretty well, we have pretty good data rate, and then sometimes when the signal quality is not very good, we'll get several errors or a period of a few seconds where we don't do very well at all. Well, no surprise, there's no intelligence to that decision. It's just random. It's just a guess. We could also check if the link is closed, just meaning if we're receiving the data correctly, and that does a little better. But at least the way we're doing it here, it doesn't really keep up. It doesn't really predict what the next condition is going to be very well. So that's okay. It's better. We can also check a link margin. That's just kind of giving us a buffer. Maybe we're allowing a little, just making sure the signal strength is good enough. And that works most of the time. And then we have another version where we say find the best scheme, and we actually allow a little bit of a, well, we have a greater than or equal to 0 here. So we're comparing the signal to interference plus noise ratio. Right now there's no interference, so just signal to noise ratio to what we need for these particular combinations of modulation and coding to work. And that one works the best yet. But we do see these outages, and we're tracking those as well. So we have 9 so far out of, with so many units of time. If we want to add a little bit more of a little bit more of a margin, make this a little more conservative, so that ideally we'll have fewer outages, but maybe slower overall transmission, not as many bits transmitted per unit time. We'll just change that from 0 to 3, so we're adding up, giving ourselves a little bit of a safety margin, and we'll see there's still some outages, maybe not as many. If we want to be, just more. Anyhow, more conservative, we can change it to 10. See what happens there. And the nice thing about this is that there are 2 things. One is that the student can edit the code, so students can explore and try their own strategies. And the other is, as great as that radio test bed is, there aren't enough radios for tens or hundreds of people to use it at once. Right now we have it set up so that one person can really use it, maybe 2 at a time. But we do have a similar exercise that uses the test beds, and we'll take a look at this. Okay, so here we have some actual signals. We have 2 signals, one on the right that is we can control its frequency, we can control its bandwidth, and with this plot on the lower left, you can see what's happening there in the frequency domain. We can change the gain or the power of the signal, so we can make it weaker or stronger. We can change that modulation and error correction coding scheme. That's not, the effect isn't obvious in the spectrum plot, but it does change the throughput here, and you can see the throughput or data rate over time. We see that we're able to make that higher, or if we're too aggressive, and it might not, we might select a combination of modulation and error correction that would work really well if the signal were, the channel were good enough. But if the channel's not, then it doesn't work at all. We can also decrease the signal strength, and it's kind of strange that decreasing the signal strength would increase the data rate, but there's actually something going on here where there are nonlinear effects that you can actually overload the amplifier in either a transmitter or the receiver or both, and that causes distortion. That even though the signal power is good, the quality of the signal is not good because it's distorted. And this is something we study. So what we've got here is kind of a tool for exploring all these things, and the ability, again, we have the ability to choose some different adaptation strategies. Right now we're early in this process, so we just have we have the capability to control the parameters, and we have the capability to observe the environment. We just haven't put it all together. So this is where this is something that if you're interested in learning more about this or the antenna range, this is something that you can do actually, fairly early in your time in engineering school. You can get involved in projects like this, and definitely people can contact me. Particularly students at Virginia Tech. Just contact me if you're interested in these projects. We have many people working on the projects as volunteers, or when you get to the second year or beyond, you can take independent study credit. So some people do that as well. Sometimes we have paid positions, but those are usually for people who've been working on the project for a while, and are already contributing to it. So this is just to give you some ideas of things that you can do. So what I'll do right now is I'll go ahead and share this. I'll go ahead and, okay, let's see. I'll go ahead and share this URL, okay? And this one will only work for the next few minutes. It's not going to be working all the time. So I'll share, first I'll share the current URL for that live exercise on the test bed. And we're working in a radio band for which the FCC does not require a license and at low power. So we're able to do this. You can go ahead if anyone would like to try that link. Actually, more than one person can use this at a time. And if you want, let's say if one person, I could do this in 2 different tabs, but somebody else could do this. If one person wants to run the program that changes frequency 1, somebody else wants to run a program that changes frequency 2, somebody else wants to change the bandwidth, you could just select one of these from the menu, hit the checkbox, and that program will run, and you'll see your program having some effect along with other people's. So you can see how this could be kind of a multiplayer game where you have two radio links trying to share the spectrum and each transmit as many bits as they can, but without interfering with the other. You could make up various rules for it. It's actually something we could use to explore how different regulatory policies might play out in practice. So are there any volunteers? Is anybody still on the call who would be interested in trying the exercise? Okay, so you can let me know in the chat, or okay, and if or you don't even have to let me know in the chat. Just go ahead and click on the URL, try sliding one of the sliders or choosing one of the programs and see what happens. Thank you for your time, and thanks for your interest in this. If you want to contact me if you have any questions, and have a good evening.